ये चालू हो रहा है।
नाही नाही, नागोडी.
Evening. Sorry, good afternoon. Good afternoon, everyone.
కదా రావట్లేదు శ్రావణి జియో రావట్లేదు నెట్ ప్రాబ్లమ్ ఫోర్ సిస్టమ్
Sir, shall we start the session, sir? Shivakumar, sir.
Audio video for
Sir?
Hello,
Yes, sir. Shall we start the session, sir?
Punita ma'am. Punita ma'am,
Yes, sir.
is it audible?
Am I audible, sir? Am I audible? Lighter.
Kumar
Yes,
sir, audible sir.
ma'am. Kanavali, ma'am.
Tell me ma'am.
Am I audible?
Yes.
Okay.
Madam, start the session, madam.
Okay, sir. Good afternoon, everyone. Today we are in final day of ATAL FDP sessions organized by Tagore Institute of Engineering and Technology, Deviakuruchi, Thalaivasal, Tamil Nadu. We are having three sessions today, session 11, 12 and 13. So now we'll start with session 11 with a topic of research challenges in robotics and their machine learning based solutions. It will be handled by Dr. S. Ramabalan sir. So it's my pleasure to introduce Dr. S. Ramabalan sir. He received Bachelor of Engineering degree in Mechanical Engineering from University of Madras in 1997. Then he obtained his Masters of Engineering degree in CAD/CAM from Madurai Kamaraj University, Madurai in 2003. Also, he received his doctorate degree in robotics from Anna University, Chennai. He has 27 years of teaching and industrial experience. He held various administrative leadership positions like principal, chairman of various committees, NBA accreditation in charge, AICTE approval in charge, ME program in charge, HOD, etc. Presently, he is working as a principal in Selvam College of Technology, Namakkal. He has served a design engineer for 1 year and 4 months in an engineering industry. He has published 4 books, namely Basic Engineering for Mechanical and Civil Department, Air Pollution and Control, IoT Based Systems, and VLSI and Chip Design. He received Best Principal Award from Association of Mechanical and Aeronautical Engineers, Tamil Nadu in 2019. He received International President's Award for Iconic Achievement, Eminent Educationist Award, and Jewel of India Award in the year 2010. He received rupees 22 lakh for doing 3 research projects from TNSC, ST, DST, and AICTE. Also, he has received rupees 24 lakhs from various funding agencies for conducting FDPs. He has also completed 4 consultancy projects worth of rupees 45 lakhs. He has guided 22 PG students and 53 UG students, and he has guided 12 PhD scholars. Now, he is guiding 3 PhD scholars for their research work. His research interests are robotics and intelligent optimization algorithms. He has published 94 research papers in various referred international journals and 6 research papers in various referred national journals. He has also presented 40 research papers in various international conferences. One of his international journal papers is ranked number 1 in the category of top 25 most downloaded papers in sciencedirect.com. He is also having 4 patents. His area of interest include robotics, intelligent optimization techniques, and CAD/CAM. So we are delighted to have him with us today to share his valuable insights. Welcome you, sir.
Thanks, ma'am. Am I audible to you?
Yes, sir, you are audible, sir.
So, good afternoon to one and all present here. First of all, I'd like to thank Professor G. Ganesan for giving this wonderful opportunity to discuss with our participants. Also, my sincere thanks and great appreciation to Tagore Institute of Engineering and Technology for conducting this very interesting adult FDP on machine learning in robotics, shaping the future of digital advancements. So now I'd like to share my PPT. I have shared my PPT. Is it available, ma'am? Hello?
Sir, not so, sir.
Is my PPT viewable?
Sir, not viewable, sir.
Yes. Now, ma'am?
Now viewable, sir.
Yes. Okay. Dear participants, let us start our discussion related to the topic research challenges in robotics and their machine learning based solutions. Once again, good afternoon to one and all present here. It's a pleasure to be here today to discuss one of the most transformative intersections in modern technology, the application of machine learning to solve fundamental challenges for robotics. So the title of our talk is Research Challenges in Robotics and their Machine Learning Based Solutions precisely defines our journey. We will not only identify the critical bottlenecks that prevent robots from operating seamlessly in our complex world, but also dive deep into the specific machine learning paradigms from deep reinforcement learning to transformer models that are providing the keys to unlock new levels of autonomy. Our subtitle is from perpetual uncertainty to intelligent action. Outlines these are. We will start with how machines see and understand their surroundings, move through how they decide and plan, and conclude with how they learn to physically act and interact. Next, we see what is the reality. To understand the fundamental challenge in modern robotics, so look at this split screen. On the left side, we have the dream, a robot operating in perfect simulation. Here, everything is known. The physics are simplified. The lighting is ideal. and every object is perfectly defined. We can run a million of trials here in the time it takes to run one in the world, and virtually no cost. So this is where we train our machine learning models. See in the right, we have the reality, the same task in real kitchen. Here physics are complex and noisy. The friction of the countertop, the flux of a plastic cup, the vibration of the motor. Sensors are imperfect. Cameras have grain. LiDAR has spurious reflections. The environment is unstructured, clutter, changing lighting, and unexpected. So this disconnect is known as simulation to reality. It is a single greatest barrier to deploying learned robotic policies in the real world. The central question for this entire presentation, so therefore to this, how do we bridge this gap? So the solutions, as we will see, are not just better hardware, but smarter machine learning. And this challenge defines our journey through perception, cognition, and actions. Look at this slide. This slide shows the sense, thing, act paradigm. Actually, to understand the challenges, we use this simple model. A robot must sense its environment, think about what to do, and act to change the world. Our journey today will follow this structure, exploring the challenges and machine learning solutions for each part. Right. Actually, where does this machine learning fit in? Traditional programming hits a wall when faced with the complexity of the real world. Machine learning is a paradigm shift. Instead of telling the robot exactly what to do in every situation, we show it thousands of examples and let it learn the underlying patterns. So this allows it to handle situations it has never seen before. Our path through this robotic model is here is our roadmap for next hour. We are going to journey through the three core components of an intelligent robot following the classic sense, think, act paradigm. First, we will dive into perception. Here the challenge is about moving from raw pixels and sensor data to a meaningful understanding of the world. We will see how the traditional vision fails and how machine learning, specifically deep learning, gives robots a powerful form of sight. Then we will move into cognition, the brain of the operation. The challenge here is decision making and planning in complex and uncertain environments. We will explore how techniques like reinforcement learning are enabling robots to learn optimal behaviors through trial and error rather than relying on rigid pre-programming. Finally, we will arrive at action. This is where plans meet physics. The challenge is dexterous, adaptive, and safe interaction with the physical world. We will see how imitation learning and advanced control policies allow robots to execute complex manipulation and locomotion tasks. So for each of these three areas, I will first show you a concrete real-world example of the challenge, and then we will dive deep into specific machine learning solution that is breaking down that barrier. So let's begin with how the robots see. This is part one. That is the perception, that is challenge of seeing and understanding. Now we begin our first deep, that is a perception. So it is a foundation. If your robo understand its environment, no amount of smart thinking or precise action will matter. Think about what a robo sees. It is not a picture like you and I see. It is a grid of numbers representing pixel brightness or a massive unordered list of 3D points from a LiDAR sensor. So this is the chaotic reality is shown on this left side. The monumental change of the perception is to turn this numerical soup into overrun model of the world. The robo needs to answer the questions like what objects are around me, where are they, where am I in relation to them. So this process of creating understanding from sensory data is a first and one of the most difficult hurdles. So in the next few slides, we will look at specific instances of this problem and reveal how machine learning acts as a translator, converting this data into intelligence. Now,
Excuse me, sir.
yes, ma'am.
Are you changing the slide, sir?
Yes, ma'am.
But it is not changing in display.
Okay, okay. So once again, I will come out and share.
Okay, sir.
Is it visible now?
Yes, sir, visible.
Just I'm changing the slide. So is it moving, ma'am?
No, sir.
Slides
It is
are.
still in first page.
Oh, it is in the first page.
Sir,
Yes, sir.
sir, do you face any difficulty? Means, kindly share your slides, sir. Our host will share the slide.
Oh.
Already the host is having the slide.
Sir, I have your slide, sir.
Yes, sir. Yes, sir.
I will present, sir.
You can run, sir. You can run the test now.
Oh, okay, sir. Okay, sir.
Now I'm in slide number 7.
Oh, okay, sir.
Okay, sir. Okay, sir.
Sir, the previous one, sir.
Sir.
Previous slide, please.
Okay, sir.
Yes, sir. I will continue, sir. Thank you. Now, see this challenge number 1. Robust object recognition. Let's make this challenge concrete with our first deep dive, robust object recognition. So look at these 3 panels, left side, center, and the right side. They all show variations of simple cardboard box. But to a traditional robo vision system, each one would be completely different object or not an object at all. The first panel shows occlusion. The box is partially hidden. A system looking for a perfect rectangular shape would fail here. The center panel Center panel shows drastic lighting changes. So algorithm relying on the consistent color and brightness breakdown. The right panel shows how the object's shape and appears to be to deform from different viewpoints. And what if the box gets a 10? See, this is a reality for a robot in a warehouse or a kitchen or in a hospital. The real world does not present objects neatly on the blank background. Traditional computer vision, which relies on handcrafted features like specific edges or colored threshold, is incredibly brittle in this environment. So a slight change, you or I won't even notice, can cause the system to fail completely. So the result, operational inefficiency, lost time, and the robot that cannot be trusted to perform seemingly simple tasks. So this is a problem that demanded a fundamental different approach. Now we move to the next slide. Sir, next slide. Okay. So this machine learning based solution for this challenge. Here we use the convolutional neural networks to tackle this situation. So let us follow the journey of our accumulated box through this network. The CNN does not receive a command like find a rectangle. Instead, it processes the image through multiple layers, each learning a different level of abstraction. In the early layers, the network acts like a basic edge detector, identifying simple shapes and colors. It is asking where are the lines and curves. So in the middle layer, it combines these edges to recognize more complex patterns. Maybe a flat surface here or a folded flap there. It is asking what textures and patterns do I see. In the deep layer, it assembles these patterns into a coherent whole. It is now recognizing these patterns together form the abstract concept of a cardboard box. So because it was trained on vast data sets containing boxes in every conceivable state, open, closed, torn, occluded, in bright light and in shadow. So it has learned the essence of boxness. So it does not need to see the whole box to recognize it. Patterns it learned are sufficient. So this is the power of representation learning. See here we provide the data in 3 layers. The CNN learns the optimal features for the task, making it incredibly robust to the very variations that doomed traditional methods. Next, we move to the next slide. Now we see the challenge number 2. Spatial awareness is a SLAM problem. Now let's tackle our second major perception challenge. Spatial awareness is perfectly captured by one of the most famous problems in the robotics, that is SLAM problem. Imagine you are blindfolded and trapped into an unknown room. Your task is to draw a map while figuring out where you are on the map. This is exactly what we ask robots to do. It is a profound chicken and egg problem. As a robot moves, small errors in its wheel rotations or in its interpretation of sensor data inevitably creep in. These tiny errors accumulate, leading to drift, where the robot's internal belief about this position becomes increasingly wrong. So the map it builds becomes distorted. Yeah, like a map drawn on the rubber sheet that is being stretched. So the robot also faces the data association problem. Is that the same chair I passed earlier, or a new one, or if it is the same chair, I can use it to correct my position. If not, I might mistakenly create a duplicate in the map. You have likely seen the impact of this challenge with the early robo vacuums that would clean hopelessly missing entire areas because their spatial understanding broke down. This is a SLAM problem in action. Next slide, please. Now let us see how machine learning provides a revolutionary solution to this SLAM problem. Here the key insight is to move beyond just geometry to semantic understanding. Look at these comparisons. Traditional SLAM on the left side, it creates maps based on solely on geometric features, corners, edges, and points. These are anonymous and can be confusing. Is this corner from a desk or wall? So the machine learning powered SLAM on the on this right side uses deep learning to recognize what those features represent. It builds a map where landmarks are not anonymous points, but recognizable objects like a desk, chair, door. So this is transformative for several reasons. The first one, semantic features are more stable. A chair might move occasionally, but a conference room door is a permanent, highly recognizable landmark that drastically reduces drift. Second one, models like PostNet can look at the scene and make an educated guess about the robot's location directly, providing a powerful starting point. The third one, the loop closer becomes much more reliable. It is easier to recognize you are back in the kitchen sorry, because you see the refrigerator and stove, not just because some geometric points match. Finally, by identifying moving objects like people, the system can filter them out, so preventing them from corrupting the static map. The result is a spatial understanding that is not just accurate, but truly intelligent. Next slide, please. So let's visualize this evolution to really cement this concept. A three-panel progression shows how the machine learning has transformed robotic mapping. Start with the traditional SLAM. So the map is spare clouds of geometric points. It answers the question, where are the obstacles? But it is brittle. If the lighting changes or a chair is moved, and the robot will get lost because it is anonymous landmarks. So the landmarks are disappeared. Now look at this machine learning enhanced visual SLAM. The map becomes textured 3D model. The robo now has photo realistic memory of the bird. This is a huge step up in the robustness. It is a difference between recognizing a friend by their skeletal outline versus recognizing them by their full appearance. So finally, we arrive at the power of semantic slant. This is a game changer. The map is no longer just a set of points or texts. It is a database of objects and their relations. The robot does not just see a point cloud, as in the previous traditional. Now it sees a desk, a door. This is a fundamental shift from mapping to understanding. So with this semantic map, the robot can now follow complex human-like interactions. So the command like go to the meeting room is no longer a geometric puzzle, a logical query. It can execute by finding the object labeled meeting room door in the map. So this is the foundation for true collaboration in human spaces. Next slide, please. We move to the challenge number 3. Now let us tackle a perception challenge that is absolutely fundamental for interaction depth perception. We consider humans do this effortlessly with our 2 eyes, but for a robot with a single camera, the world is flat and ambiguous. Look at this workshop scene. The robot without depth perception, this is just a single flat image. It has no way of knowing that the wrench is closer than the screwdriver in the background. So when it reaches out, it does not know how far to reach. The result is a miss or worse, a collision. So this is a curse of 2D image. So it's why robots traditionally relied on expensive lidars or complex stereo camera setups. But what if we could teach a robot to infer depth from a single image, just as our brain? It can make educated guesses from molecular cues. So this leads us to another powerful application of deep learning. Next slide, please. Now we see the machine learning solution for this challenge. The solution is to use a specialized convolutional neural network for monocular depth estimation. So we don't program the rules of perspective. We show the network examples. So we train the network on millions of image depth map pairs. It learns that objects that are blurrier, higher in the image frame, or have some specific texture patterns that are usually further away. It learns that pixel representing a car's height weight, head weight has a different depth than a pixel representing the road behind it. So the output, this output is a beautiful and color-coded depth map. Suddenly from 2D image, the robo has a rich understanding of 3D structure of its environment. It can now see the range is close and wall is far away. So this inferred depth is accurate enough for navigation, obstacle avoidance, and significantly improving the grasp success rates, all without needing an expensive lidar. This is the point here. Next slide, please. Now we'll see the challenge number 4. Limits of vision, the need for the task. See, we have supercharged robo vision, but there are fundamental physical properties that vision alone cannot perceive. See, this brings us our final perception challenge. the need for touch. Look at this page. To a camera, it looks perfect. But is it a foam and ready to be picked up, or is it right and requires a gentle touch? Vision cannot answer all these questions. So, robo without a touch would apply a standard rigid grip, force and crush this fruit. So this is a fundamental limit of vision. It is an excellent remote sense, but it tells us nothing about the material properties. We only learn through physical interaction, softness, slipperiness, weight, and temperature. So for a robot to truly interact with the world, it needs a sense of touch to complement its sight. Next slide, please. This is a machine learning solution for this. So we give the robo a sense of touch with a high resolution tactile sensors, but the raw output from these sensors is just a grid of numbers, a pressure map. So this is where machine learning comes in again to interpret what the robo is feeding. We train the model. Often a network good with the sequential data like an RNN or tactile data paired with the outcomes. It learns that certain spreading, soft pressures, pattern means squeezing a ripe beach, while sharp localized vibration means. So the result is a robot that cannot only see a beach, but also feel that it is ripe and instantly lighten its grip to a safe level. Next slide, please. Now we move to the part number 3, cognition, brain of the robot. You know that we have seen how the robot perceives the environment. So we arrive on the code of intelligent cognition, the brain of the robot. This is where a perception meets action, where raw sensory data is transformed into purposeful behavior. Actually, cognition enhances everything from simple decision making to complex reasoning. So it's what allows a robo to not just see a cluttered table, but to plan how to navigate around it. Not just detect an object, but decide how to manipulate it. So in this section, we will explore how machine learning is revolutionizing robotic cognition, moves from hard-coded logic to adaptive, learn intelligence that can handle the complexity and uncertainty of the real world. Next place, please. Now we'll see the challenge number 3, motion planning in the complex environment. See, consider this factory scenario. A robo arm needs to pick a part from a cluttered bin and place it on an assembly line while avoiding the other parts, equipment, and even human workers. This is a classic motion planning problem. The challenge here is astronomical. With a 6 degrees of robo, we are searching through 6-dimensional space of possible configurations. So add in moving obstacles and the need for real-time performance and traditional planning algorithms often either run too slowly or get stuck entirely. So this is not just an academic problem. See, in real factories, inefficient motion planning leads to lost productivity, while unsafe planning can lead to dangerous collisions. So we need a smarter approach. Next slide, please. See the solution. Instead of programming, we show the robot what to do. Learning from demonstration allows us to capture human expertise directly. So in the this first panel, an expert physically guides the robot through optimal motion. The robo records not just the position, but the entire trajectory, the accelerations, the delicate around the obstacles. The magic happens in the learning. We don't just record and play back. The machine learning model underlying policy, mapping from censored states to appropriate actions. It learns the intent behind the motion, not just the motion itself. Actually, this is why the ma'am, please move to the previous slide. Okay, thanks. So this is why the third panel, when we slightly change the situation, moving the pin or using a different part, robot can still succeed. So it has learned essential strategies of reach into bin while avoiding the obstacles rather than memorizing one specific path. Now move to the next slide, ma'am. Okay, thank you. Now we'll see the challenge number 4, learning complex manipulation skills. Learning complex manipulation skills like flipping a pancake. This task seems simple to us, but it represents a nightmare of physical complexity for traditional robotics. Look at the physics involved. We have flexible object that deforms under gravity and conduct forces. So we have complex slip dynamics between the spatula and pancake. So we have to deal with the fluid behavior of the batter, and we cannot even see the entire pancake during the critical flipping motion. So traditional control approaches would require modeling all these physical phenomena with exhaustive precision and essentially impossible task. So it is a very impossible task. So because the equations would be incredibly complex and small modeling errors would lead to complete failure. So these were learning-based approaches, so they are true power. They can discover successful strategies without needing explicit physical models. Next slide, please. Move to the machine learning solution. We are using deep reinforcement learning. So it provides the framework for robots to learn these incredibly complex skills through massive parallel trial and error. Here, how it works: we place our robot in a realistic simulation environment, a virtual kitchen with accurate physics. We define a reward function that captures what we want: successful flip gets plus 1,000, dropping the pancake gets 100, and we add a small time penalties to engage efficiencies. So the robot starts completely ignorant, taking random actions from millions of trials across parallel simulations. The neural network policy gradually discovers which action sequences lead to higher reward. So it learns the precise rest motions, optimal flip timing, and how to recover from mistakes. So this is a key insight. We are not programming. The solution is we are creating the conditions where the robot can discover the solution itself. Next slide, please. Now we are visualizing the DRL for manipulation. See, the transformation through DRL training is nothing sort of remarkable. From the left side, we see the robot during the each training. It's clumsy, uncoordinated and fails spectacularly, success rate is essentially zero. Average reward is deeply negative. Now look at this right side. After millions of training episodes, the same robo performs with elegant, efficient motions. The flipping action is smooth. The pancake lands perfectly, and the success rate is 99%. So this progress graph tell this a full story. Next slide, please. Now we move to the challenge number 5, multi-robot coordination. Let us scale up from single robot to teams. Multi-robot coordination presents enormous challenges. So in this warehouse scenario, we see multiple autonomous vehicles trying to navigate shared spaces while completing their delivery task. The problems are fundamental. Without coordination, robots create jams, get stuck in deadlocks, take inefficient routes, and frequently have near collisions. Traditional approaches using centralized planning or simple rules quickly break down as the number of robots increases. So we need a more scalable, adaptive solution for this challenge. Now we move to the solution. Now we use the multi-agent reinforcement learning. It provides the framework for robots to learn coordinated behaviors. And the key insight is centralized training with decentralized execution. After training, each robot can operate independently using only its local sensors. Yet the system as a whole exhibits sophisticated and coordinated behavior. Next slide, please. Now see the MARL performance results. This is before the situation and after the situation. The performance improvements with MARL are dramatic. So look at the before and after metrics. What you can observe from these two scenarios. See here, the system throughput more than doubles. Collision rate dropped by 98%. Task completion time is cut by nearly 2/3, and energy efficiency improves significantly. The learning, there's a learning curve shows that the coordination emerges relatively quickly and substantial improvements happen within the first 10,000 training episodes. So the system then gradually refines its strategies, asymptotically approaching near optimal performance. Next slide, please. Now we move to the challenge number 6, human-aware navigation. See, as robots move into human environments, this is a new challenge. It is not enough for robots to simply avoid collision. They must navigate in ways that feel natural, predictable, and comfortable to human beings. So the problems we see here are fundamental. Robots that cut too close to people, block pathways, make sudden movements, or ignore social conventions like personal space, create anxiety and reduce trust. Our metrics show that so what is available in the current system? The current systems score poorly on human comfort. Also the safety is not ensured. So this is not just about a technical navigation. Say it is about understanding and respecting the human social norms and expectations. So we expect the robots also obey the social norms and the expectations of the human being. This is very interesting and difficult challenge. Now move to the machine learning solution. Next slide, please. Here we use inverse reinforcement learning. See here, if we use it, it addresses this challenge by learning from human experts instead of trying to manually specify all the complex rules of socially appropriate navigation. We saw the algorithm of how human navigate comfortably. See here the process works in the reverse of normal reinforcement learning. See here we observe expert behavior, humans moving naturally through crowded spaces, and work backward to for what reward function they must be optimizing, what values do human place on personal space, on predictable motion, and efficient but comfortable paths. The learn reward function captures these implicit social norms. So when we then use this reward function for a robot navigation, the resulting behavior feels natural and comfortable to humans because it is based on how humans actually behave. Next slide, please. Now we see the IRL social navigation results. The improvement with this IRL is immediately apparent. The traditional navigation focus solely on the shortest path, collision avoidance, resulting in mechanical, sometimes starting behavior. But this IRL based navigation produces smooth, predictable trajectories that maintain comfortable distances and respect social conventions. So that now the robot moves in the ways that feel natural to humans because it has learned from human examples. Next slide, please. Next slide, please. Okay, thank you. Now we move to the challenge number 7, long horizon task planning. Now we assume one situation. Let's consider the challenge of this one. Complex task that require multiple steps, conditional logic, and handling failures. A simple example like this: prepare breakfast actually involves numerous subtasks with complex dependencies. The planning difficulties are substantial. Some steps depend on others. You cannot pour cereal before getting the bowl. There are resource constraints. You can only carry so many items at once. Temporal constraint matter. Milk should be added last. And we need to handle failures gracefully. See, the traditional task planning approaches struggle with this complexity, especially when dealing with the uncertainty and partial observability of the real world environments. Next slide, please. Now we use hierarchical reinforcement learning to give a solution for this challenge number 7. It provides a framework for tackling complex long horizon tasks through temporal abstraction. The key idea is to decompose the problem into multiple levels of decision making. So at the highest level, we have the manager that operates on a course time scale. At the lower level, worker policies operate on the time scale, expecting primitive actions to achieve the current subcodes. The hierarchical structure makes learning tractable for a complex task So the manager learns efficient task decomposition, while the worker becomes proficient at specific skills that can be reused across different high-level tasks. Next slide, please. Now we see the HRL task execution results. The advantage of using HRL are substantial. See, this is a flat reinforcement learning, and this is a HRL approach. This HRL achieves much higher success rate on complex tasks while requiring significantly less time. About 4.7 times more simple efficient. But the real power emerges in the additional capabilities because skills are learned separately from task decomposition. Robots can perform zero-shot generations to new tasks that require similar skills. So they can compose known skills in novel ways and recover efficiently from failures by replanning at the appropriate level of abstraction. Next slide, please. Now we move to the part number 4. See here we have seen how the machine learning revolutionizes individual components of the robotics. Now let us consider the ultimate integration, end-to-end learning. Instead of separate modules for perception, planning, and control, we train a single massive neural network. As in this figure, it directly maps raw sensor inputs to motor commands. The benefits are profound, By eliminating hand-designed interfaces between modules, we reduce error propagation and latency. The network can learn optimal representation that serve multiple purposes simultaneously. Next slide, please. Now we move to the simulation to reality gap. This is a simulation environment. This is a real-world deployment environment. You can compare the results. See, it represents one of the most significant practical barriers in the robotics. See, look at these quantitative comparisons. A policy that achieves 95%, 98% success in simulation might initially achieve only 42% in the real world. The reasons are fundamental because simulation physics are simplified. They cannot capture all the complex friction, deformation, and contact dynamics of the real world. So the sensor models are idealized, missing the complex noise patterns and calibrations errors of the real hardware. Visual appearances also are perfect, but unlike the messy lighting and textures of the real environment, this performance gap is not just theoretical, it translates to weeks of additional adaptation time and extensive fine-tuning for our real-world deployment of the robots. Next slide, please. Now, we will give the machine learning solution for domain randomization. This domain randomization, it gives an elegant solution to real problem. It is simulation to the real world problem. So instead of trying to make simulation perfectly realistic, so we train across thousands of randomized simulation variants, each with different physics parameters, visual appearances, and sensor characteristics. See here key insight is that by exposing the model to extreme variability during training, actually we force it to learn essential invariant aspects of the task. But the model cannot rely on specific visual features or exact physical parameters. It must learn from the fundamental principles. So the results are dramatic. The policy arrives in the real world already robust to the variations it will encounter. So let's move to the next slide. See the data bottleneck. It is a fundamental economic and practical concern in robot learning. Actually, real-world data collection is an extraordinarily expensive and slow. So between robot cost, human supervision, hardware maintenance, and safety constraints, we are all limited to hundreds of trials per day at a significant cost. So meanwhile, simulation can generate millions of trials per day at minimal cost. So with no safety concerns or hardware wear. But there is a catch. Simulation data lacks the fidelity and complexity of the real-world experience. So this creates a fundamental tension. So we move to the solution. Next slide, please. So two emerging paradigms like tackling the data bottleneck, offline reinforcement learning and self-supervisory learning. So this offline reinforcement learning, it allows us to learn from existing data sets of the robo operation, like studying a textbook, rather than conducting new experiments. So we can mine years of operational logs to discover new scales or to improve the existing ones without any additional real-world trial and error. See this self-supervisory learning enables robots to create their own training signals from unlabeled data. So by predicting what happens next, see here that together we are combining these two approaches. So together these approaches can improve the data efficiency by 10 to 100 times, dramatically reducing the amount of expensive real-world data required for the learning. Next slide, please. Now we'll see some of the research scopes. How to use machine learning for doing robotic research. See, scope is vast and transformative. This is meta learning aims to create robots that can adapt to new tasks with just a handful of examples. Imagine a robot that learns a new household chore after seeing it done just once or twice. So world model research seeks to enable robots to learn compact, predictive models of their environment instead of expensive real-world trial and error. So robot could imagine the consequences of their actions and plan efficiently in their internal simulation. So here the causal inference, it represents perhaps most profound challenge. Moving beyond correlation to understanding the truth. It allows the robots to reason about the interventions. If I push this object, it will fail. So the transfer knowledge across fundamentally different environment. So this is a very good scope for doing the research. Next slide, please. So another research scope is human-robot interaction. So human-robot interaction, we can use the natural language groundings this affective computing. So we can use it, allows the robots to read the human emotional states and intents from subtle cues, views in voice, facial expressions, and body language. So this enables more natural social appropriate interactions. Next slide, please. Another research scope is this embodied AI. It represents a paradigm shift in how we develop, evaluate robotic intelligence, and rather than testing isolated capabilities. So we create rich, interactive simulated environments where agents must demonstrate complete sense, think, act loops. So next slide, please. Now we'll get into the robotic research. Actually, if you are inspired to contribute to this exciting field, so here is practical pathway to get started. So this beautiful thing about modern robotics research. You don't need $1 million lab. Most of the tools are open source and freely available. So start with the foundations, strong programming skills, and the essential mathematics. Then dive into the core tools like ROS for robot software architecture, BiBullet for simulation, and modern deep learning frameworks. The implementation phase is actually here crucial. So there is no substitute for hands-on experience, reproducing published results and building systems yourself. So start with a simple project and gradually increase the complexity. Now move to the next slide. The previous one. Yes. See here also the scalability actually is the important one in the robotic research. So take care of that. Please move to the next slide. See, let's follow this machine learning powered warehouse. Through a typical day, starting with the morning, a shift at 6 a.m. Robo initializes using its semantic SLAM system to verify the environment. It has not changed overnight. It receives the first batch of orders, 47 VRT shipments. The first order presents a classic change challenge, mixed kitchen supplies with varying fragility and shapes. The traditional systems would struggle with this diversity. But our robo uses CNN, convolutional neural network based recognition to identify each object type and adapts its graph strategy using learned tactics practices. So next slide, please. See this case study. This is important case related to the dynamic replanning and human collaboration. See, as the morning continues, we see the robot learned adaptively in action. When a fill blocks the main ISL, the robot does not freeze or require human intervention. Instead, it uses its learned navigation policies to immediately replan an alternate route, lasting less than a minute compared to what would have been a 15-minute work stoppage. The latter, when a human worker needs to assess the same self, the robot demonstrates its social navigation skills. Using inverse reinforcement learning, it yields appropriately maintains a comfortable distance and smoothly resumes the work. So all while making the human feel comfortable and respected. See here the high comfort rating and maintained efficiently. So how machine learning enables true collaborative workplaces. Sorry. Next slide, please. So this is another case related to the learning and improvement during operation. So we can use machine learning. It will reduce 12% operation time. So next slide, please. See here, if you use machine learning for this case study, this end of the day performance metrics for this one. See here, 99%, 99.3% is success rate. And here, zero damage rate, significantly. So it shows how the machine learning techniques significantly outperform both traditional automation and the manual operation. But the real differentiator are the machine learning specific advantages. Robo autonomously resolve. See here, 89 problems that would have required human intervention in the traditional system. Most importantly, the robo ended the day smarter than it started. See, having mastered 15 new of the type and optimized its behavior based on the base experience. Let's move to the next slide. See, this is another case study related to economic and operational impact. So in this case study, if you use machine learning, we can reduce the 65% of the labor cost. 92% is reduction in damage cost. Actually, it is in the just 14 months, so we can get a lot of benefits. Please move to the next slide. So this is comprehensive recap. So this table summarizes the transformative impact of the machine learning across perception and cognition challenges. See, in perception, we have moved from fragile rule-based system to robust learned understanding. So achieving near perfect object recognition and spatial awareness while eliminating the need for expensive sensors like LIDAR in many applications. In cognition, the shift is even more dramatic. We have replaced complex hand-coded planning algorithms with the systems that learn from demonstration, coordinate through multi-agent learning, and navigate social spaces by understanding human preferences. The performance improvements are staggering, doubling throughput, while nearly eliminating collisions and achieving human-level comfort and shared spaces. Most importantly, see here, these are not isolated improvement. They compound, creating systems that are fundamentally more capable, adaptable, and efficient. Go to the next slide. See, in action and integration, we see how the machine learning enables robots to not just think, but act effectively in the real world. So text series manipulation moves from programmed trajectories to adaptive sensory-driven policies. Please move to the next slide. See, this machine learning based robotic transformation matrix. It shows how this fundamental paradigm shift enabled by machine learning. We are not just making the incremental improvement. We are changing the very nature of what is possible in the robotics. Move to the next slide. This is related to the future trajectory from automation to autonomous. See, as we conclude our technical journey, this roadmap shows where we are headed. Today we have systems that achieve superhuman performance on specific tasks, but still require human supervision and struggle with the generalization. In the near future, we will see some robots that generate across domains, handle edge cases autonomously, and coordinate in multi-robot systems. So that exhibit emergent intelligence. The emergence of the foundation models for physical intelligence will be as transformative for robotics, as they are copying the language. So we have a lot of the models, language training models. We can use them. So the long-term vision is nothing less than human level physical intelligence. The systems that can acquire new skills through observation, reason about physical cause and effect, and the continuously self-improve. So the enablers we need from safe real-world learning to casual reasoning. It represents some of the most exciting research frontiers in artificial intelligence today. So what is clear is that machine learning has fundamentally changed the trajectory of the robotics, turning what seemed like science fiction just a decade ago into the achievable engineering targets for the coming years. So next slide, please. So we arrive at the end of the journey. The central powerful message is that the future of the robotics is learned, not programmed. So we have seen a fundamental paradigm shift. We are no longer limited to painstakingly telling a robot how to perform every micro task. Instead, we can define the goal and provide a learning environment. And through machine learning, the robot discovers how for itself. So this has turned problems we once thought we were decades away, like dexterous manipulation or social navigation, into active and rapidly advancing research domains. So here we have built the crucial bridge between the perfect world of simulation and the messy reality we live in. So, and we are now developing the foundational models that will enable robots to be generalized, not specialized. So the ultimate goal is not to create the autonomous machines that replace us, but to build intelligent partners that collaborate with us. The final final image captures this perfectly. Human and machine working together, each doing what they do best. So this field of accelerating and breath taking pace. So at the next decade, we will be defined by tuning this research challenges into real-world solutions. So, dear participants, thank you for your time and attention. I look forward to your questions.
Thank you, sir. Thank you so much, sir. Participants, do you have any questions? Please post your questions, or you can ask questions now.
Excuse me, sir.
Yes, ma'am.
Excuse me, sir.
Hello.
Sir, can you say some real-world examples for machine learning-based robots, sir?
Ma'am, already in the slide I have shown a lot of case studies, how we are using the machine learning. For example, handling a food itself, it is not just handling. It is touching the fruit and learning about the physical parameters involved to handle that fruit. So all these examples we already discussed now.
Excuse me, sir.
Yes, ma'am. Yes, sir.
May I ask a question?
Yes, sir.
Sir, very good presentation. First, I want to congratulate you. You have given a very good presentation.
Okay, thank you.
My question is that how this robot and this ML can be useful for financial sector.
What, sir? Identify?
How this ML technology and this robotics will be useful for finance. I am working in HSBC company. Okay. Hello.
Yes, sir. Yes, sir.
I am working in HSBC company. So I would like to know how it can be useful for finance sector.
Finance sector.
Yes.
The finance sector, actually, lot of data is available, sir. So the system can be trained with the millions of the data already from the history. The system will predict the market share. Maybe in future, machine learning based system will predict and tell in what stocks you can invest, like that.
And how it can be useful for share market.
Yes, sir. Actually, in the share market, it will not change. It will not give much change, sir. Already, some AI-based tools are available to predict the share market, the challenges, and suggest some solutions. So this will
Yes.
help us, sir. This will help us so we can earn more money.
Okay. Can you share some applications?
What, sir?
Can you share some applications
What application, sir?
for this share market prediction?
Oh, sorry. I'm not much aware of that share market things, but I know there are some AI tools which are useful for human beings, so they can use them. Even lot of websites are also they're advertising. They can help using these machine learning AI tools, so they can help to the people to invest in the market, sir.
Okay. Thank you, sir.
Thank you. Thank you.
Thank you. जिंदगी में क्या होता है एक एक सेकंड नहीं ये मैं राहुल भी कर रहा हूँ
Any other questions, participants? Okay, we'll share SARS material, PPT material, and his mail ID in chat box. Please verify it and follow it. Now, shall we end the session, sir?
Okay, but once again, my sincere thanks and lot of appreciation to the organizers of this great AICTE FDP in Tagore Institute of Engineering Technology, especially to the Professor G. Ganesan, sir. So thanks a lot, and thanks
Thank you,
to
sir.
the organizing team. Thank you. Thank you,
Sir,
Ananda.
actually, we are grateful for your time, effort, and your knowledge you have shared with us today. Thank you once again for making these sessions both informative and inspiring, sir.
Thank you. Thank you.
Thank you, sir.
Thank
Thank
you
you so much, sir.
very much.
Thank you, sir. Thank you.
Kindly fill your feedback form and take your assessment, which have been shared in WhatsApp group. And for the next section, for the next session, join at 3:35 p.m. Thank you.